me a very theoretical paper. Yeah. So I can't see anyone else's video, but if you can see my screen, maybe could you just type in the chat yes? I'm going to actually just like check. Can you see my screen?
Oh, no, Peter, we can't see your screen.
No, okay. Okay, cool. Now I think
it's good now. Yeah, yeah.
Okay, great. So I chose this paper because it deals with, I think, like, it deals with the problem that we have, especially in real world data sets, which is you have data points in your data set that are missing values. So you basically, this only is relevant to multi-dimensional data sets where your features, like the space of your data set is multiple features, and you are missing values within it. It's funny because I think you could think of like a really obvious case of this is actually supervised learning, where your label is your missing value. But this is, I think this is a more general setting, and it's more assuming that you have a set of features, which is your, let's say, call it your feature space, which is usually denoted by X in the literature. And you have both, for each data point, you have a set of features, but also you have a set of features missing in some of the dimensions of your feature space. And I'm just going to make sure I don't miss anything in chat. I think as like a really basic introduction, this problem deals with the parent class of this problem that the paper is addressing is generative modeling, which is when you have a finite set of samples. Funny enough, in this paper, that like all the theoretical guarantees have to do with having an infinite number of samples in your data set, but you have a finite number of samples from some what you consider underlying fixed distribution, and you want to recover a model of that distribution so that you can sample from it. And that sounds very mathy, but there's like a lot of different cases in which you would want to use that. Like, for example, I found out that GitHub has just recently released a new feature for developers who and you can sign up on the waiting list for it, where what it does is you would type in like a comment above a function, and then you would type in the function and its inputs, and it would guess what the rest of the function would look like. So it's like autocomplete on steroids, and I think it uses GPT-3 trained on code to train the model. So that's an example of a generative model, because what it's doing is it's actually generating code. And so it seems like a very mathematical problem, but there's a lot of use cases for something like that that exist in the world. And so this example is actually this generative model. What it's assuming is that you have in a lot of generative models, you assume that you assume that you are completely, you have no information about the samples you want to generate. Like you want to generate the classic example that we've seen maybe from a couple of years ago is you train your data set on you train your model on a data set of bedrooms, and you want to generate new realistic images of bedrooms. Usually you don't have any pixel values, for example, of the new bedrooms. But in this case, they assume that you do. And you want to estimate what the other pixels are going to be given those pixels and your previous data set of training set points. And so that's kind of like the problem set that they're addressing here. And the specific problem that they're addressing is that an important element of this problem is that the reason for missing pixel values could be dependent on like the underlying mechanism that's generating the picture of the bedroom, for example. And in that case, you can't just if you don't take that into account during training, then you're going to get like biased estimates of what those values should be, like what those additional pixel values should be. So that was like a pretty long-winded explanation of it, but I actually thought there's a good diagram in this paper to kind of explain what I'm talking about. And the diagram itself seems kind of magical to me, I have to say. Like if they're actually, I was like, is this really, how did they even get these results? But I think there's some like secret sauce in this experiment that we'll go over later that I'm not getting. Like maybe they have like they already know what the underlying distribution is, like the parameters of the underlying distribution in terms of like not the specific parameter values, but what the parameters are. So anyway, this their first experiment is on a set of a set of synthetic data sets that they've created that are like, I think they're mixtures of Gaussians or something like that. Let's just yeah, it says we generate 3 synthetic data sets with nonlinear data generation processes. For all data sets, the observed variables, which are x1, x2, x3, are generated from latent variables. Sorry, I'm just, where they do say somewhere what the distribution is. Maybe it's over here. Anyway, it's some distribution. I think it's like Gaussians or something. But so the contours illustrate what the ground truth distribution is. And if you look at the leftmost plot on your screen, where it says training set, basically what it shows you is that they sample uniformly from the training set, but there's an underlying mechanism which hides points in specific regions. And so you can see like in data A that they're only getting maybe a fifth of the overall support, or like kind of like the overall support of the data set's underlying distribution. And then they show 3 models where the rightmost is theirs. And by taking into account that there could be this underlying dependent mechanism which is hiding points in specific regions, then they're able to recover the entire distribution over the feature space, which is pretty cool. And you can see how like other methods which don't take into account this fact that you could be biased, you could have bias, that like they have a bias. Like for example, this PVAA fit, you can look at for data set B, you can look at the training set, and it seems like the set that is learned is just like a small expansion around the training set, as opposed to showing more of the shape of the true underlying distribution. So that was like kind of a quick
that
introduction.
seems almost too good to be true, right?
Now let's go through the paper.
Sorry, Peter?
I think the first important idea, there's a couple of interesting ideas in the paper. The first one, or like I think the key insight of the paper, is that to do this in an unbiased manner, you need to have identifiability guarantees for the model that you're training, where I'll just go quickly to a definition of, because like this identifiability is one of the key ideas of the paper. It says, here's the definition of model identifiability. It says, assume that where theta is your model parameters, assume that you have some parameterized distribution over your feature set X. And this distribution takes, the parameters in this distribution take on values from some parameter space, large omega theta. Then a model is identifiable if there's basically if it's unique in terms of the distribution that it expresses. So there's no other distribution that can be expressed. There's no other set of parameters which can express the same distribution. And we'll go over it later, but the key idea that they show is that they try to create an identifiable model in order to be able to come up with unbiased estimates for filling in the missing values in a data point that they're trying to fill in the values for, where that process of filling in those extra values which are missing is called imputation. And let's see, where do they first introduce? I guess it's over here. So I think we'll try to go over this part a little bit slowly, because I think it's like another one of the key ideas in the paper, which is there's different mechanisms, missing mechanisms. So a missing mechanism is the mechanism or way by which it's decided that which values within a data point are missing from all the values that are like all the dimensions within a data point. And there are three different cases. The first case they call missing completely at random, MCRA. And that's when the mechanism for like dimensions having missing values is completely independent of like the feature values themselves. So a good example of that in a neural network would be dropout, because dropout values are sampled from a different distribution than the feature distribution. And then the second one is called, where is it? So that was MCRA. The second type is missing at random, MRA, which assumes that the missing data mechanism is independent of the values of unobserved data. So basically, whenever you get a data point, you know that the conditional distribution, which is like which determines the missing mechanism. So like in this case, your missing mechanism is dependent on your feature values, like whatever small x is in the sample, but it's only the ones that you can see in that sample. And in which case you have all the information you need to also learn the missing mechanism. And if you know the missing mechanism, then you can try to impute values as well. And then the last one, which is the focus of this paper, is the one that's called missing not at random. And this is when the missing mechanism is conditioned on unobserved variables as well. So basically, within your data point, you have values that are missing, and the reason why they're missing is also whatever value they took on. I hope that all makes sense. And like they say, it says in this last case, which is the case they focus in on the paper, ignoring the missing mechanism will result in biased imputation, in which case you'll get like a biased, like an incorrect estimate for what the missing values are with respect to the underlying distribution.
Hello.
Yeah, we went over identifiability, and I think we'll go over these plots in a second, because I think it's better to. Oh, yeah. What's up, Dirk?
Hey, can you hear me?
If you want, you can post the
Yes,
question.
Doug, we can hear you,
Okay,
Doug.
perfect. Yeah. If you go to the intro
sorry.
again there.
Yeah.
The introduction of the paper, where they mentioned the assumptions they make. So the page we just covered there. I think the secret sauce here, like these results do look almost too good to be true, but I think the one huge assumption they make here, or I guess the thing counting in their favor, is they know the exact probabilistic mechanism that decide which data is missing. If you know that, if you know exactly what causes the data to be missing, you can get quite exceptional results like this. I've seen it as well in studies where, for instance, you're trying to study what's the effect of smoking on survival. If you know that people who smoke are going to die sooner, therefore they will be more likely to be missing, you can get quite cool results, and it's almost magical how you can learn things that you didn't have in the data at all. But this is quite a huge assumption, this understanding exactly why the data is missing. I think oftentimes you'll have missingness in the data, but you don't know exactly why it's missing or what was the exact process, and that's where it gets hazy. It's also heavily dependent on assumptions. If you make the wrong assumption about the missingness, that will introduce another kind of bias, essentially. So that's probably the secret sauce here, but it's still quite impressive to see how well you can recover things you didn't see if you make a few assumptions and they are correct, I guess.
But do they make the assumption here?
Because, yeah, I was going to say, yeah, go ahead, Arvid.
Yeah, because it looks like, if I understand the paper correctly, they actually model it based on the values they observe, and I think they also use some covariates that might not necessarily work alongside the missingness criterion, I think.
Yeah, so I would say let's keep going through the paper, and I think it will come out as an answer whether they're making this assumption or not a little bit later. Let's see. So we're still in the introduction. They talk, like they say, their method provides identifiability guarantees, which are important for being able to discover the underlying mechanism, basically the underlying distribution. But then they say, like, we have to relax these assumptions that we make to provide for the proofs that they use in order to create an algorithm that's practical. And honestly, I don't see like that much of a difference between, I was like, from a practical point of view, it doesn't seem like they're actually making proposing a very different model than what's already out there, but maybe I'm wrong. And they just talk about how this missing not at random is something that's much more common in real world data than these other cases. And then they talk about what their contributions are. And I just highlighted this in purple because I was like, this is the worst acronym ever in terms of like representing what the model is actually called. So the model is called Deep Generative Imputation Model for Missing Not at Random. And the words, the letters that are used to create the acronym GINA are G, like generative imputation, and not at. So I was just thinking that, why did they, it feels like a bit forced, but this is a silly point that I just wanted to point out. It's like, why did they force this act? Why did they even need an acronym? Just call it what it is. Anyway, and let's jump into the problem setting. So like we talked about identifiability already, and I'll just read it out. It says that basically model is identifiable if different parameter configurations imply a different probabilistic distribution over the observed variables. And it's the whole point is with identifiability guarantees, if the model, where is it? I'm just reading it out. Assumption is correct, then the true generative process can be recovered. So I think this is one of the underlying massive assumptions of the paper and the proofs and everything, is that the massive, which is a general massive assumption in deep learning. So it's not like you can fault the authors for this. This is just, which is like that the parametrization of your model can express the underlying distribution. And that's what they mean by if the modeling assumptions is correct, and they actually list it as one of their assumptions in their proofs.
Is it saying that it's uniquely expressing the situation, which is a bit strange, right? Because if you think of any neural network, I think that the weights are never one-to-one. I think you can always recombine your inputs and outputs, and would get essentially a different set of weights doing but the model would do the exact same predictions, which is kind of flying in the face of that.
But would it do it over the entire feature space?
I'm pretty sure. Isn't there such a thing that's the way you prove that there is not a single minimum for your weights of any neural network, because you can always just flip any inputs around and you essentially get a the same problem just with different weights and there's the same results?
Yeah, I'll look that up. I've never heard of that, but it does sound like it sounds very possible / makes sense. But in this case, actually, I think that this is a separate assumption than identifiability. So they're saying that you have to, if the parameterization of your model is such that one set of parameters can express only one distribution, and the parameterization is the same as the underlying distribution, then you can recover the underlying distribution.
Also, so essentially you break the symmetry of your parameters by forcing some prior onto them.
Mm-hmm.
Oh, that might make sense, yeah.
And so, okay, basic notation. Let's get into it. There's a lot of notation and it's quite confusing. So the feature set is X, large X. And then they introduce this index set, which is an index. There's an index for each dimension of each point in the feature set. So if your feature set was like a 32 by 32 image, there would be 32 times 32 indexes. And so they separate. They say the feature set X is composed of like a feature set for each dimension, essentially. I don't know if you necessarily have to break it down by dimension, but anyway, basically there's subsets that are indexed that compose the entire feature set. And so they break down the feature set into a set of actually observed variables and a set of unobserved variables, where the entire feature set is the combination of the two. And then they introduce another, so XO is the observable variables. They call O the observable pattern, and then U is the missing unobserved variables. And I actually think that, and you guys can correct me if I'm wrong, that U is not that the values are always unobserved, it's that they're partially observed. So XU is just the part of the feature set where you can have missing values. Anyway.
So does it mean that XO would be always available without exception?
That's what I think, but honestly, I think if for me to fully understand this paper, I'd have to read it over like a couple times over a week or two.
This is usually the notation they use, yes. I don't know if this is the same kind or if they mean the same thing, but usually when they write about missing data problems in Bayesian literature, at least, they would write X as all the data. And if some of the X's are missing and some of them are observed, you would have X missing and X observed. So I think what they mean here is XO is the set of all the X's that are observed, and XU are the ones that are, it's essentially NA values or blank values, XU, that can be anything. But I might be wrong.
Yeah, sorry.
XO and XU would be dependent on the sample. So XO would be a different set for the second survey I'm getting.
Yeah, for each of the samples, yeah.
Okay.
Yeah, and this is why if you integrate out over XU, you're essentially integrating out all the possible values that XU can be. So if you just had one missing X value and you believe that X value came from a normal distribution, you'd essentially just integrate out over that whole normal distribution.
Yep.
You're sort of marginalizing out the missing values, which is very easy to do in theory, but these are a lot of complex integrals if you have lots of missing values, basically. So it's a nice theoretical result that you can never actually use in principle, which is why you have to do imputation or something like that.
Yeah, that makes sense with this integral down here they're talking about.
Yeah.
And so the last variable that is part of the problem setting is R, which is the missing mask. So like a dimension of the feature sample is observed, then the mask value is 1, and if it's unobserved, then it's 0. And so the problem setting is, I'm just going to read it out. It says, suppose that we have a ground truth data generating process denoted by this probability distribution here, from which we can obtain partially observed samples. So you get these samples, which is you see some observed variables and you have the missing mask telling you which ones are missing. And we also have a model to be optimized denoted by P of, and the parameters are theta and L, where theta is the parameter of the reference distribution, the underlying distribution P of X, and lambda is the parameter of the missing mechanism P of X of R. So this part is where I think they're not actually assuming that they know the missing mechanism. They just have the they learn the model for the missing mechanism. And they say our goal is to establish the identifiability of basically this disjoint distribution. And then given the knowledge of this joint distribution, to impute values. So given X of your observed variables, to figure out what your unobserved variables are, or in this case, it's saying like to figure out the likelihood of your unobserved variables, which is very similar. And so, okay, 2.2, let's see. Yeah, they say call it their name. Okay, so again, they just point to the first two cases, which is when missing data is missing completely at random. So there's no relationship between the unobserved variables and there's no relationship between the feature space and the missing mechanism, or when the missing mechanism completely dependent on the observed variables, then you can perform maximum likelihood estimation based only on your data. So you don't have to take into account the missing mechanism, essentially. You can just learn the underlying distribution. And oh, this is one thing that I underline. It says they say, in practice, machine learning algorithms on the observed variables can be done using expectation maximization algorithms. And I guess they're just showing that you can identify the optimal parameters using expectation maximization algorithms. But I don't think that in practice you see expectation maximization in deep learning that much, because it's, I think, too computationally expensive. Or maybe you just can't calculate the optimal parameters at each step of expectation maximization.
I'd agree with that. I've never seen EM in deep learning applications. What I have seen is I think Radford and Neil wrote an article once. Usually, when you run into a problem where you have to do expectation maximization and you find that's too expensive, the other thing you can do is MCMC, like Markov chain Monte Carlo, which is usually a lot less expensive. And I have seen some cases where they use MCMC to estimate parameters for a neural net, for a deep learning kind of model. Neural nets, MCMC is usually also one of the benefits of using it is that it makes missing data problems really easy, because you're already drawing samples. So it's sort of like you get multiple imputation for free almost. So this is probably just an interesting aside they're making.
Would MCMC be more expensive typically? I thought EM typically relies on some variational distribution that to some extent you're making approximations at that level.
It depends, yeah. It depends. This is where it gets quite problem specific. Sometimes EM algorithm is a lot less expensive. Sometimes MCMC works better. There's no one easy solution for all of them.
No free lunch, as they say.
Yeah.
Damn it.
This is also luckily why none of our jobs are going to be completely automated soon, because there will always be this human in the loop thing about, do I use EM algorithm, do I use MCMC? If the one's running for 20 hours, the other one might only run for 3 hours, something like that. And lots of papers to be written on when to choose which one.
Let's see what Google has to say about that.
Yeah. So anyway, so basically they have this point where they're just saying, in the case of these two other data missing mechanisms, we already know how to calculate the optimal parameters in theory. And then they say, in the case of missing not at random, mechanism, Rubin, in another paper proposes that you jointly optimize these two likelihoods, and by doing so, you should recover an unbiased. You'll be able to recover an unbiased distribution, basically. And this method is called selection modeling, and they refer back to it, which is why I'm pointing it out a couple bit later in.
But when you say it's an unbiased distribution, does it depend on specific assumptions about the structure of the of the generating process, the data generating process?
I think what they say is there are multiple challenges if we want equation 1 to obtain a practical model that provides unbiased imputation. So I guess there are additional assumptions that you have to make, which they talk about in the proof, to get unbiased imputation.
So that would be your choices of theta and lambda effectively.
Yeah, and actually how they relate to the data set and the missing mechanism. And they say, first, we need a model assumption to be consistent with the real world data generation process. Again, this like both trivial and completely non-trivial assumption that the model you choose is able to express the underlying distribution.
Yeah.
Okay, it has to go.
Yeah, that's quite a big assumption, but I guess it's more so, it's more a problem when you're doing completely parametric modeling, where you might assume a log normal distribution and the actual one is actually normal or something like that. Here, I don't think they're making that stringent distributional assumptions, so you can sort of get away with this. If the model can explain the real world data adequately, this assumption won't hurt you that much. And again, this is usually an assumption you have to make, and it will always hold, right? If the model isn't able to explain the data well, whether there are missing data or not, you're going to have a bad time. It's just that the more quirks you have, the worse things are going to be. And missing data is quite a big quirk, because you're losing a lot of information, essentially.
And that's very true. The second assumption, which we've gone over a couple of times now, is that the model needs to be identifiable to learn the underlying process, which leads to unbiased imputation. And I think this is okay. And then okay, I don't know about you guys, but when I was reading this paper, I was like, okay, this all makes sense. And then they jump immediately into variational autoencoders and their identifiability. And it was like, I don't see why you're putting this here. Why are you jumping into this so soon? But basically, in their method, they propose using a VAE with a specific prior described by this distribution here. And so what this whole section is about is that there is in the literature a VAE that is identifiable up to equivalence permutation, which I actually don't know what that means. I didn't have time to look it up. If anyone does know what it means, feel free to say. But there's like one massive, there's some assumption, again, that unfortunately I didn't have time to look up, but that's part of this, which is that you have access to some auxiliary variables, which are observed. I don't know what those variables are, but if anyone's interested, the whole point of this section is basically to motivate their proposed method after they go through all their theory, where they they propose using this type of VAE because it's identifiable, and their whole point is that you need the model to be identifiable to create unbiased, to impute values in an unbiased manner.
So here they sort of argue that identifiable is equivalent with saying the data distribution must come from this exponential family. Is that fair? Or the Z?
The Z is a latent variable. So basically, this is a good time to go up to here. Basically, they assume that the entire underlying process is generated by a set of a latent distribution, Z. And so whatever values Z take on determine like with uncertainty what values X, like the X is going to input feature, the features are going to take on, which determines the missing mechanism R. So I didn't say that very well, but this is why they have all of all these diagrams have a Z in it, because like an additional assumption, which is not like actually pointed out in their problem setting, is that they assume that there's some latent distribution Z that that all the variables are conditioned on, maybe at least in some way. So you can see all of except F is one where it's not conditioned on latent variables. But actually, so yes, I think you're right what you said, Arvid, that Z is
because that seems to be one of the reasons why their results on the training sets were so good, right? So if you imagine they have this Gaussian distribution, and you only observe ever a slide of it. So the missingness mechanism is very strict in the sense that your data density that is ever observable is 0 at some point, right? So, and I think we had previous papers, right, that probably show that if somewhere your data density is 0, you can't possibly learn something from it. You sort of will have to extrapolate from the things you can observe into that. Yeah. And why does this extrapolation work here? Probably because the assumption is that the data generation process has a particular form that is sort of conserved over the observed and unobserved part of your data, and that might force the results to be good just because it's a true assumption by
design.
By design, exactly.
Yeah.
Yeah, I do think that's what's happening. Still impressive, but it's not a case you'll run into in reality quite often, where you don't even know what the generating process is.
Yeah.
Yeah. So that's what this whole that's why this whole section on VAs is in here, because you're assuming that the data generation process is conditioned on a latent distribution. And I just wanted to quickly go over like what these different models are expressing, and basically and go through H, because they talk about H later, which is that, so you have some latent variable distribution, and it along with the uncertainty inherent in the distribution of X determines X, which then determines the missing mechanism for X1. And I think a key component of all of these, except for the last two, is that, except for F, G, I, and J, is that like one feature value within a data point doesn't determine another, like those cross arrows, because they do mention a few times that their analysis kind of breaks if there's a dependence between feature values. I think that's true, but we'll go over very quickly the guarantees that they provide. Okay. So establishing model identifiability under missing not at random. Okay, so their first definition is, we say they create another different definition of identifiable. Okay, And then they go into sufficient conditions for identifiability under missing not at random. And we say we give sufficient conditions where the model parameters data can be uniquely identified by Rubin's objective. So this is where I was thinking that they used this objective that we saw up there. So yeah, so over here they're providing the assumptions that you have to make or you have to meet in order for the in order to use that objective we saw above, in order to learn a distribution which is able to do unbiased imputation. It's very like deep explanation in a way. Yeah, I'm not going to go over this in a lot of depth, just because I feel like it has a lot of math which takes longer than, I don't know, like a couple sentences to explain. But so I'll try to go through it. So the first thing they do is they say, we're not going to go through all of the cases that they have in this set of graphical models, which is over here. Instead, we're going to focus on H.
Oh, just a quick random question. I see they keep on referring to like Rubin. Is that the Rubin book from 1987?
I think so.
Referring to
Donald Rubin, right?
Yeah, I think Rubin and Little wrote a book on missing data in 87. I'm just wondering whether that's the one they are referring, or
let's see. Well, we can look at Donald Rubin.
Because they keep on just mentioning him by surname. So I was wondering if it's
1976, inference and missing data, formalizing subjective notation. That's who they're talking about.
Okay, thank you.
Okay, we're one page above. Okay, so I'm going to close this and I'm going to get rid of this search. So the first assumption they make is about the data, and the assumption, I think, is basically that the data, the features X are not conditionally dependent on each other given Z. So that's what's expressed here, and that's what's expressed in which of the, I guess it says it down here. That's expressed in figure 1H, which is this one over here. So there's no connection between X1 and X2. So you first make that assumption, and then you have a couple of assumptions that you make about the data. The first one is the one we keep talking about. We've said a couple of times that the ground truth parameters of the distribution belong to the model space, the modeling space. So the true distribution parameters are in omega. And then the second two, I'm just going to read what they said here, because for me, these were like a little bit hard to understand. So they're saying assumption A2 is that the probability of the observed variables should be at least identifiable for a collection of observational patterns that form a partition of I. So if you look at assumption A2, they're saying there exists a partition of I. So like to me, that means there's a set of indexes within the number of indexes of the input features for which like the parameters of theta are identifiable. And that was actually a bit confusing to me, because it goes back to the thing we were talking about in the problem setting of whether O is a fixed set or is it dependent on the sample. Because based on this, it's saying there exists a partition of I. So it's like a fixed number of indices for which the parameters of the model are identifiable. If anyone has any ideas about that. And then the second point is the third assumption is that A3 ensures that this joint distribution should be positive for certain important patterns. So I guess this has to go back to something along the lines of like, for the variables that we do observe, you can also recover the joint distribution. Like I guess it's saying that within the observed variables that you actually see in your data set, the probability of like the unobserved variables should be non-negative. I mean, strictly positive. Anyway, so, and then they say, so if you meet this data setting D1 and then the assumptions A1, A2, A3, then your model is identifiable. That's the whole point.
Is that what is sort of actually broken in their example they apply to when they say that the density is strictly positive, but actually they make such a cut that it's not strictly positive in their in their synthetic data?
Well, in their synthetic data set, the distribution is it's over the entire continuous domain, like it's over like R2. So there's a non-zero distribution. I mean, not non-zero likelihood of every point in the distribution, I think.
But does it have to be observable? I might have misunderstood that. Sorry. So the positivity is saying that any value of XO and XU can potentially appear.
Well, I think it's not. I'm not sure. Let's actually go over it for a second. I'm just gonna check the time. Okay. Oh, we don't have. Actually, we don't have a lot of time.
Oh, sorry. No, never mind then.
Yeah. So I'm just gonna do some real quick. Go over some stuff real quick. So basically, the first setting, they show in the first setting that you can get an identifiable model, and then they say in the second setting, if you can define some kind of like mapping that has an inverse between the parameter space that your model is in and the parameter space that the data is in, then your model is still identifiable. It's something along those lines. But if you want to know more, I definitely encourage you to read the paper. And then they basically say, you know, we're making some really hard assumptions about the problem in terms of like hard to satisfy assumptions. And what we actually suggest is you learn a VAE with the prior distribution that's described in that section we just talked about, and the missing mechanism is described by this Bernoulli likelihood model over here. And that's where I was thinking to myself, just how much of a contribution is this practical method, like the thing that they're really suggesting? Just because it doesn't seem like there's a lot of, if I were to take a naive approach to the problem setting that they provided, it probably would look something like this, in my opinion. So that's where I was like, where does all of this like really cool math in terms of proofs and guarantees come into providing a practical solution, which is not the obvious one for the problem setting? And I think the answer is that I haven't understood fully the connection between the two, but that's something that is just something I was thinking about.
It's potentially the extension on Z, on the shape of Z, right? So how I think one could rephrase the parameterization of Z in terms of they maximize the entropy of Z. Essentially, you observe your moments of some distributions, potentially quite complicated, but then you extend it in a maximum entropy way outside the observed space. And I think it's this, what do you call it? Putting a prior on that seems to work well in practice, because it's also on their real life data, it seems to be working well, which is philosophically maybe not a bad assumption to make. Take the minimum information assumption.
Well, I'll go through the experiments and then I'll ask about that. And then they just provide a way of calculating like the likelihood of the observed information, and then to do imputation given their model. And so there's three experiments that they run. The first one is on a synthetic data set to basically show the like how well their model performs at imputation. And yeah, they have these qualitative plots which just show that their model is able to like correctly generate samples in the part of the space which isn't observed. But as we said before, this seems like too good to be true in a way. But I think it has to do something with maybe it's that, as you guys have suggested, that the latent variables Z1, Z2, and Z3 follow exactly the distribution of the VAEs prior that you assumed. Yeah, Mahad, go ahead. I saw you raised your hand. But, oh, no, you're allowed to talk. You can talk. Okay, I'm gonna just keep going. Okay. So one of my criticisms of the paper is I actually don't think that in their experiments they experiment.
Hello. Oh, right. Cheers, Peter, for a very good talk. Back to the question that you had on why they suddenly jumped into variational autoencoders when they had established a good theoretical proof on how you could get good form of imputations. When I say good form of imputation, which means it takes into account all kinds of randomness which get introduced whenever you have some form of biasness within your data, just simply because some aspects are missing. So the way I understand is variational inference, which is the part that is the major component of variational autoencoders, is a form of latent variable modeling in it that you have a proxy distribution that is trying to measure a real distribution, but the variables that it constitutes are sort of unknown. You have to make a guess on that. So I would assume that's where the key component of how this relates to modeling of hidden variables in the form of data that is missing. So like you don't know which bit is missing, but you assume, okay, maybe it's this, maybe it's that. Like we saw last week when we were trying to talk about causation, where when you're not sure an event is happening simply because there's a correlation, but there could be a missing random variable that you don't know it's sort of related. So I would say this way of using variational inference sort of gives you the freedom to model your hidden variables. That's what I had in mind as to why they picked this method. What's your opinion on this? Cheers.
I think that makes a lot of sense. In this case, it's less that I think that the method that they're proposing makes a lot of sense. I just also see that like the major contribution is the theoretical side of it, and to me, it doesn't motivate like a very it doesn't motivate a very different solution than the one that you would just try anyway. But I think what the idea that Arvid is suggesting that sounds like you're introducing some kind of maximum entropy objective into this is more of the contribution, and that's something that I just haven't understood in the math, but doesn't mean it's not there, and I just probably have to read this paper again. Just because I'm wary of time, I want to go quickly through the last two experiments. So as I was saying, one of my complaints or things that I didn't like as much about the paper was I don't feel like they explain the problems that they're actually, like the inference problem that they're performing in each of the last two experiments very well. So the first one has to do something with, they have this data set of user song ratings, and they're trying to, I guess, figure out what the song ratings are for songs that they don't have the, like for songs that they don't have the rating for. I'm guessing that's what it is, but it's not stated explicitly in my opinion. But anyway, what they show is that the mean square error of their method in comparison with previous methods that use a very similar approach, it seems like state of the art in this right now is using VAEs in one way or another. They show that their method performs best by a certain amount. It's hard also to gauge like how good that is. And that's like another thing I was thinking is just that it seems like this paper is very geared towards people who are already doing research in this problem, which makes sense. But at the same time, it means that you have to read some other paper just to get an idea of these benchmark problems that you test imputation on. But anyway, so their method does better than the other methods in terms of, I guess, figuring out the rating of songs that where a user has only rated a couple of songs. And then the last experiment is around education. And they have this data set of student performances on a multiple choice test. And they basically want to see how their problem does on the test set, I guess, at figuring out like which problems that a student on the test set would not answer, I'm guessing, and then also like which ones they would answer correctly and incorrectly. And then they also apply their method to a decision-making problem, which is that you're given a history of questions that the student has answered, and you want to suggest a next one for them to answer, with the idea that that it will help them learn the most. So they're using maximizing the information reward of the next question that you propose, and their metric for that is that if the student got the answer correct, then the next question should be harder, and they have these metadata labels of which questions are hard. And so like I think if the next question is harder, it jumps up in difficulty by maybe like 1 or 2, and then if it's less hard, then it goes down in difficulty by -1 or something along those lines. And basically what they're showing is that their method is better on the first task of figuring out like which questions students would get right in the test set, and then also at the on the second task of posing a harder question when the student gets something right, and a less difficult question when the student gets something wrong. Yeah. Yeah, sorry I rushed through this last part. But now I just want to open up the floor for questions, comments, anything that you want to discuss in more detail. Maybe I'll go back to that nice diagram. Yeah.
I mean, it seems to be generally a big improvement, right? So, by that standard, that is definitely a great paper.
Yeah. Yeah, and it seems like maybe that possibly it's just probably a problem that was maybe considered too hard in the past and never really addressed, and so they found a good way to address it.
Yeah. Or at least make good assumptions, or ignoring those parts of the problems that are generally impossible, which is of course fair, because in practice you have to make a choice somehow.
Yeah.
How did you find the paper? Any chance?
How did I find the paper? I mean, in general, I thought it was well written. I really like this diagram here because I think it at least illustrates the problem that they're trying to solve in a good way.
So what I meant is, how did you find out about the paper?
Oh, sorry, that's not
my German.
Yeah. So the paper I found, it was in what was the I think it was in NeurIPS at 2021. And I chose the paper because obviously, like, we have a real world data set that we work with at NPlan, and there's a lot of missing values. So I'd never read papers about imputation before, so I wanted to choose a recent paper on imputation.
Oh, cool.
And it was, I think, one of 2 papers at NeurIPS last year, in 2021, that was on imputation. So it's not a super well explored topic. Great. I'm gonna stop sharing and stop recording.